if P2 refines P1. No, this is the net of partition. If you want, Dave, you can say this. That's what you're talking about. Yeah. These two things are going hand in hand. So if P2 has more points in it than P1, that is to say, if it's a fixed interval and you're chopping it into more pieces, actually this doesn't have to be true, doesn't it?
No.
You can leave one. You can have one clunker subinterval that is, make sure that the two norms are the same, and yet this really does refine it. That when we study the Stieltjes integral, this will be an important factor. If the norm of the one is definitely smaller, it means that this happens, but this doesn't imply that, right? You see what I'm saying? If I have two partitions, and I've got some points here. This is P1,
Right.
and I have the same points, of course, for P2, and then I add another point there. That's P2. The controlling interval size looks to be that one. It's the same as also the norm of the partition is the same. However, P2 has more points. It contains P1, so it's finite. Right? What we'd like to do is have some way of comparing these two Cauchy sums based on different partitions. Well, here's the great idea. Calculate the Cauchy sum for the common refinement. In other words, every point that's in S1 is put into the mix, and every point in P1, every point in P2. Okay? So P1 union P2 is a refinement of both P1 or P2, either P1 or P2, right? Refines them both. So how close would then S sub P1 union P2, which is the sum from I equals 1, not necessarily n plus n, because there could be some repeated points, right? We have to go to a new index, t, say, f sub x I minus.
T is what, the maximum everything?
No. They could be duplicates, except for 1 point, and it would be one more than n. Or they could be, right?
Oh, okay, I see. Yeah. Okay. I see.
These are two totally different ones. Maybe totally different. This allows any amount of overlap.
Okay. Yeah.
This one puts them all together. So you don't know what the overlap is. So you know that
There's some.
T. I'll tell you, this is true, Dave.
Yeah.
That's true. Right?
I'm seeing that.
Okay. That's true, but that's about all you can say. So there's the Cauchy sum that corresponds to the common refinement.
Tom, does SP sub 1 doesn't have to have less points than these two? They can't be equal?
No. This can be bigger, smaller. We're not saying anything. This was just how things are refined. I wanted to clarify what a refinement was. Okay? These two can be arbitrary. They can share, they have to share A and B, but other than that, the intermediate points can be totally different in both sets, P1 and P2, or they can be the same, and anywhere in between. Okay, now, in the general case, there's some difference. When you union them up, you get a partition that has all the points in either one of them. So in general, that's finer. It has more points than either one, right? Okay. Now, if you go out and pick a delta so that the norm of the partition P1 is less than the delta required to keep the function variation no more than epsilon on any subinterval. If we do that, here's what we do. I say, I don't want the function to vary more than epsilon on any one of the subintervals in my partition. How do I do that? Uniform continuity says that if I pick an epsilon, and the function is uniformly continuous, we know it is, then there's a delta of epsilon greater than 0 that exists that ensures that. If I keep the norm of the partition below the delta of epsilon that's given by uniform continuity, then on any subinterval, the function will never vary by more than epsilon. Right? Okay. So, we don't know what the sum is, but we know that the function isn't going to move more than epsilon on any subinterval. Now, consider adding one extra partition point, say, to P1. We'll draw a blow-up of this. It'll be obvious. I think I can explain this. Here's a blow-up of a subinterval. Okay, there's many subintervals. Here's a particular subinterval, the xi. So this is in fact where we evaluate the function for the Cauchy sum, right? What if we refine the partition? Well, if we add a point, it has to be somewhere. So suppose we put it there, right? So we have a new partition. Now, this is delta x1, and this is delta x2, say, right? From here to here, here to here. All right. The new calculation, the new sum with the new partition with the 1 point added, instead of this rectangle going into the sum, what goes into the sum? This rectangle and then this rectangle, right? What's the additional area? Is there ever less area? What if thing was going down? Have to think about that.
Yeah.
But don't worry about it. This case, what's going on? Okay, you can see this little blob here of area gets added due to the refinement. How big? What's the biggest that this could be? Let's be ridiculously extravagant. Well, first of all, we know from the delta epsilon condition for uniform continuity, we're keeping the partition below the delta, so the variation this way can be no more than epsilon, right? We better think this through. Yeah, epsilon. So the additional area here then is the area has to be less than epsilon times delta x2, right? Let's be ridiculously wasteful. Let's just put b minus a in there. Okay, that's going to work for everybody, isn't it? Because that's the total length over which we're integrating. Right? Okay, well, what if we do this again over here now? Now we add a little bit of this, okay? I claim I don't have to change this. The vertical variation, the variation is still less than epsilon. We've nailed that down. The variation within a subinterval is never more than epsilon. The length of a subinterval, the total of all the subintervals is never more than b minus a. So no matter how many additional points we add, the extra area is never going to be more than epsilon times b minus a. B minus a is finite because it's a finite interval. So when epsilon goes to 0, how much area are we really adding? None. Right? You agree? All right. So what have we shown? I think what we have shown is, let me call the sum, just as a shorthand, sum for partition P1 minus the sum for partition P1 union P2 absolute is less than epsilon times b minus a. The same thing can be said of the sum for P2, right? P1 union P2 is a common refinement. P1 and P2. So the original P1 and the refinement sums differ by no more than this. This differs by no more than this. So S P1 minus S P2 is less than or equal to, well, we're going to do the same trick again. Here we go. SP1, you've seen this now a few times. So slam some absolute value bars in there with the triangle inequality. And so this would be epsilon B minus A. This is another epsilon B minus A. Add them together. 2 epsilon B minus A.